Oxidation of the alkene happens by two methods. Either I can add two OHs to the carbons of the alkene. In this case, I will be forming either cis diols or trans diols. Or I can break the double bond of the alkene and make carbonyls in there. And the carbonyls can be either an aldehyde, ketone, or a carboxylic acid, depending on the strength of the oxidizing agent. Adding OHs can either be trans or cis. So let's consider the trans method in there. To make a trans diols, this is a two-step reaction. The first step, you need to use a peroxide. And the peroxide is a system that has two oxygens that are connected to each other. The R can be any R. It can be a CH3, it can be a hydrogen, it can be a metachlorobenzene. So if it is a metachlorobenzene over here, then it's going to have this structure, and we're going to call it metachloroperoxybenzoic acid, which we're going to abbreviate it as MCPBA. And this abbreviation, you're always going to see that. Now, whenever this reacts in presence of an acid, you're going to end up cleaving the peroxide and releasing this oxygen over here. This oxygen is the one that is going to be inserted between the carbons of the alkene, and you're going to end up getting the epoxide. The mechanism, you are not responsible for the mechanism of the reaction. So all what you need to do is just to break the pi bond and insert the oxygen of the MCPBA in order to make the epoxide in this case. But pay attention whenever you are doing this, because the stereochemistry is going to be retained. So let's say, for example, if you start with a trans alkene, then the epoxide and the substituents around the epoxide need to remain a trans. They cannot change. In this case, if you start with a cis alkene, then the substituents around the epoxide, they have to be a cis substituents. Now, the second step, you already know this one from chapter 8. We've talked about the ring opening of the epoxide in presence of acidic and basic medium. So if you want a diol in this case, you can use either the acidic or the basic medium, and you can open the ring, and you can form a trans diol. Please review this reaction. This is the ring opening of the epoxide in acidic and basic medium, and you can use either water in presence of H+, this is the acidic medium, or you can use the water in presence of the OH-, that is a basic medium. In either one of these cases, you will be forming a trans diol. Let's go ahead and have an example here. So you have your alkene. Now, there is no stereochemistry here around the alkene, so I don't have to pay attention to the stereochemistry there. So the moment you see MCPBA, this means that around the alkene, I'm going to go ahead and insert an oxygen in there, break the double bond, and make the epoxide. Once you make the epoxide, you can have ring opening in presence of an acidic or a basic medium. So if you're doing a basic medium, we said that the base is going to attack the less substituted carbon, open the bond, form a negative charge, and then you're going to have a solvent that protonates that negative charge, and you're going to end up getting your diol in that case. On the other end, if you're doing it in acidic medium, then the first step will be the protonation of the oxygen, and then water is going to attack the most partial positive carbon in the cycle. As we mentioned, this oxygen is positive, so this means that each one of these carbons is going to be positive. This carbon is going to be partial positive, this carbon is going to be partial positive. So this carbon over here is going to be the most substituted carbon, and because it is the most substituted carbon, now the nucleophile is going to come, it's going to attack, and you can do a simple hydrogen shift in there, or you can use any base in the solution, like another water. So another water can come, take that extra hydrogen, any base in the solution, and you're going to form your diols. If your alkene is locked in the cycle, then in this case, you're going to form a trans diol, something like this over here. So see if the alkene is locked in the cycle and use the MCPBA, this is how it looks like. It's this oxygen that gets inserted between the carbons of the alkene. So you need to consider stereochemistry in this case because the epoxide can either attack or can either form from the back or from the top. So if it forms from the back and from the top, you have to consider both of those, specifically when you have a chiral center. So here I do have two chiral centers. So these are my two chiral centers. So you have to consider the stereochemistry. That is the first step of the epoxide. Now, once you form the epoxide, use the ring opening of the epoxide in presence of either acidic or basic medium. Here I'm using the basic medium, so the base is going to attack the less substituted carbon, open the bond, and it's going to attack from the opposite side of the epoxide. So it's going to attack from the top. The epoxide, the stereochemistry is going to be retained, so it's going to be at the back over here, and then you are going to protonate, and you're going to end up getting your products in this case. And for our products here, we're going to have these two are going to be enantiomers. Now, in order to get the cis diols, you're not responsible for the mechanism of any of these reactions in there, but you are responsible to know the reagents. Now, in order to produce cis diols, we're going to use a strong oxidizing agent, like for example, MnO4, and this is the Lewis structure of MnO4. It does, of course, exceed the octet. Mn is a transition metal, and we're going to use also the osmium tetroxide, which has a similar structure in there. Okay, now both the MnO4 and the osmium tetroxide, both they are going to approach the alkene. So both are going to approach the alkene from the same side. And when they approach the alkene from the same side, the oxygen are going to add from the same side to the alkene. So when the oxygens add from the same side to the alkene, you are going to end up getting a cis diols or cis OHs in there. The reaction reagents are KMnO4 in presence of water and NaOH. This is the first one. Or you can use osmium tetroxide in presence of sodium hydrogen sulfate and water. Or you can use osmium tetroxide in presence of tertiary butyl peroxy acid, tertiary butanol, and OH. All of these reagents, you're going to see them, and all of those, they do exactly the same thing. They allow the oxygens to add on the same side to the carbon double bond carbon. You break the double bond between the carbons in there, insert those two oxygens on the same side, and then the oxygens get protonated by the solvent. Now let's go ahead and do a couple of examples. You have first to be familiar with these reagents. KMnO4 is a strong oxidizing agent, and when it's coupled with sodium hydroxide, you are going to add cis diols. Sodium hydroxide is a must for the cis diols. If the sodium hydroxide is not there, this is going to be a completely different reaction that we're going to talk about as we proceed. So the first thing that we're going to do is highlight the alkene, and then go ahead and introduce the two OHs on the alkene. And the OHs have to be on the same side. So go ahead and introduce them on the same side. Because it is not a chiral center, just show them either both up or both down. Don't show both because they are the same. So showing the structure like this or showing the structure like this, these are both the same because you don't have a chiral center. Same thing for the osmium. The osmium tetroxide does exactly what KMnO4 does in presence of a base. So again, we are going to highlight our alkene, and we are going to introduce two OHs on the alkene. Now, introducing the two OHs on the alkene, this carbon over here, is not a chiral center. So in this case, what I'm going to do is I'm going to introduce the OH being up here and in plane here, plus, because you're going to form enantiomers in this case. So you're going to end up having your OH here, and you're going to introduce your OH is going to be at the back. So you're going to end up having a chiral center in this case and a pair of enantiomers. This is the only chiral center in there. And the reason why I didn't consider the stereochemistry of this carbon, because this carbon is not chiral to start with. So I'm going to add the OH to be up and the OH to be down in there, and the other OH is going to be in plane. Now for MCPBA, we are introducing an oxygen to make an epoxide. And I have this example here just to let you know that you are going to keep the same stereochemistry of the substituents on the alkene. So if the alkene substituents are cis, then in this case, the stereochemistry is going to remain the same, and they have to be on the same side. They have to be on the same side. However, your epoxide is going to be either on the top, so you're going to form your epoxide on the top, or you're going to form your epoxide at the bottom, at the back in this case, but the stereochemistry of the substituents around the alkene have to remain the same. If they are on the same side, they have to remain on the same side whenever you make the epoxide. Oxidation of alkenes happens in presence of an oxidizing agent. And the oxidizing agents are ozone, KMnO4. These are strong oxidizing agents. However, you have two types of oxidizing agents. You have a strong oxidizing agent, and you have a mild oxidizing agent. Now, the mild oxidizing agent will form aldehydes and ketones. So you're going to end up getting aldehyde, and you're going to end up getting ketones in there. This is with the mild oxidizing agent. With the strong oxidizing agent, the hydrogen of the aldehyde will be oxidized, so you're not going to end up getting an aldehyde. You will end up getting a carboxylic acid instead of the aldehyde. Ketones cannot be oxidized further, so ketones will stay ketones, but if there is any aldehyde, then the aldehyde will turn into a carboxylic acid. Now, the mild oxidizing agents are either ozone in presence of dimethyl sulfide or ozone in presence of zinc and water. These two are examples of mild oxidizing agent. And the way that the reaction happens is you are cleaving the double bond. So you are breaking the double bond in half, and you are sticking an oxygen to each end of the double bond. As simple as that. So in this case, what I'm going to end up having is, don't add carbons. So I have a CH3 and I have a CH in here. So you have your CH3, you have your CH. This is where you broke your double bond. So you have your CH3 and you have your CH. Go ahead and stick an oxygen to one end of the double bond. Okay, this is an aldehyde because there's a hydrogen in there. So this is going to be an aldehyde. You don't have to write the hydrogen, but I'm just throwing the hydrogen in there just to show you that with mild oxidizing agents, aldehydes, they stay the same. They don't get oxidized further. Plus, the other end of the double bond in there has how many carbons? It's 1, 2, and 3 in the double bond. So this is going to be 1, 2, and 3. Here you go. And then stick another oxygen in there so that I would know if I want to go backwards, I would take this oxygen here, this oxygen there, and diffuse those two parts of the double bond together into one double bond. So I would know how many carbons my structure have. Here, my structure is 1, 2, and 3 and 4 and 5 carbons. I will end up having here also another aldehyde. And the aldehydes with mild oxidizing agent, they stay as aldehydes. So here I'm forming two aldehydes. The oxidizing agent is going to cleave all the double bonds in the structure. So I don't have to say it's in excess because it's going to go ahead and cleave everything. Zinc in presence of water is also a mild oxidizing agent. So those two are an example of mild oxidizing agents. And those mild oxidizing agents will make aldehydes and ketones, depending on how many R's are there on the alkene. And if you have a hydrogen on the alkene, then this means that you're going to end up having an aldehyde. So this is a hydrogen here, then I know that this end is going to be an aldehyde. This end here is going to be an aldehyde. This one is going to be an aldehyde. This one is going to be an aldehyde, and this is going to be an aldehyde. And this here, it's going to be an aldehyde as well. This is the simplest form of aldehyde here, which is formaldehyde. So let's go ahead and cleave those double bonds and add an oxygen into each end. So you're going to insert an oxygen here and an oxygen there. So we're going to start by having a double bond O with two hydrogens. Okay, so this is this part over here. And then let's go ahead and continue. I'm going to end up having a double bond O. And this is my carbon. This is my second carbon. So I have my first carbon here. And then I have my second carbon. Let's highlight that second carbon. So this second carbon is there. And then I have a double bond and then oxygen. That's it. So these two carbons, I broke them off the chain. So they are not connected to the chain now. So these two carbons now are separate. And these two carbons are separate as well. Plus, I'm going to end up having a carbonyl over here. And two carbonyls actually, and all of those are aldehydes, and the aldehydes are going to stay the same. They're not going to get oxidized further. Plus the last portion of the double bond, which is a double bond O connected to 1, 2, and the 3 carbons, including the carbon of the carbonyl. So this is it. So this is going to be the 3 carbons, and you have an aldehyde. So breaking this structure, cleaving the double bonds of this structure by a mild oxidizing agent, see how many fragments did it give me? It gave me 1, 2, 3, and 4. These two are going to be the same. Let's have another example in here. Still, we are working with a mild oxidizing agent. So you're going to break every double bond in the structure. You're going to break the double bond here. You're going to break the double bond there. So breaking the double bond is going to end up making the portion which is at the bottom, okay, that is going to be broken over here. And I'm going to introduce two oxygens in there. So I'm going to end up having the lower part of the molecule. And then the upper part of the molecule, you're going to have your carbonyl in there, and then the carbonyl. So that put them like this so that you can go backwards and take off the oxygens, and then you can fuse the double bonds into one double bond. And then I'm going to end up having a double bond O over here. And then the last portion is the oxygen there and the CH3. So these are my products in there. I formed one. Let's highlight it. I formed one. This is all one product. This is two product, and this is a third product. Now, if I'm working with a strong oxidizing agent, all strong oxidizing agents will oxidize the aldehyde. So if you make an aldehyde, that aldehyde will be oxidized into a carboxylic acid. So it's going to go exactly the same way in there. So you're going to break the double bond, and you're going to break the double bond in here. Okay. However, if you form an aldehyde, make it NOH. The strong oxidizing agents are KMNO4 in presence of water. Notice here I don't have an NaOH. If I had an NaOH, then I would end up adding cis diols. So no NaOH in here, just water, or ozone in presence of peroxide. These are the only two strong oxidizing agents. So my product in this case is going to be the carbonyl. Okay, there you go. I'm going to end up having a carbonyl here and a carbonyl here. And pay attention not to add any carbons. So I do have a carbon here. This is the carbon. I do have a carbon here. This is a carbon. And then I have a carbon for the double bond, and this is the carbon for the double bond. So this is going to be my structure in there. However, notice how many aldehydes I have. I have an aldehyde here, and I have an aldehyde there. So immediately, what you're going to do over here is turn those aldehydes into a carboxylic acid. Let's have another example. And I am reacting this with ozone in presence of peroxide. This is a strong oxidizing agent. And the alkene that I have here is a terminal alkene. So I'm going to end up breaking my alkene. And if I'm breaking my alkene, I'm going to form two parts. Now, the first part is going to be a ketone. Just to stick an oxygen to each end of the double bond. Stick an oxygen here and stick an oxygen there. And the second part, is going to be a double bond O. Now, on that double bond O, there are two hydrogens in there. So see, those hydrogens are going to turn into an acid because we are working with a strong oxidizing agent. Ketones cannot be oxidized further, but the aldehydes are going to be oxidized into a carboxylic acid. If you have more than one hydrogen, then all the hydrogens are going to be oxidized. Now, this structure here is a carbonic acid. And the carbonic acid, this is called carbonic acid, and carbonic acid is very unstable. And this carbonic acid is going to dissociate into carbon dioxide, CO2, and water. So what you're going to see, you're not going to see carbonic acid. You're going to see a ketone, and in your structure, or in your product, you are going to see carbon dioxide and you're going to see water together with the ketone. Now, because these are inorganics, we don't show them, so we just show the portion of the ketone in there. But know that the reason why we don't show the carbonic acid, because that acid is going to be completely unstable and dissociate into carbon dioxide and water. Every time I have a terminal alkene, then I'm going to end up getting a carbonic acid. Let's have another example. And now I am doing in KMNO4 in presence of water. Again, no base, so no cis-thiol. KMNO4 is a strong oxidizing agent, so I'm going to start by breaking this double bond, breaking this double bond, and breaking this double bond. Now, I know that these two are terminal aldehydes. They're going to turn into terminal aldehydes, and these are going to be oxidized further into carbonic acid. This one is going to be a ketone. There is no hydrogen in there. So let's go ahead and write the carbonic acid first and then make it carbon dioxide and water. So I'm going to stick an oxygen to each end of these carbons. So, or each end to the double bond, not a carbon. So I'm going to end up having my carbonic acid here, plus that is going to be a carbonyl. This is going to be NOH because I have a hydrogen here that's going to turn into NOH. And then I have my ketone. So I'm done from this portion. And then I have a hydrogen here. So I'm going to end up having a double bond O. This is going to be my OH. And then that is going to be a double bond O and another OH in here because I do have a hydrogen. So every time you see a hydrogen, that's going to turn into a carboxylic acid. And then I do have two hydrogens on this end just to stick an oxygen in there. So that is going to be a double bond O and then OH here and then OH there. Now this one and this one are going to turn into carbon dioxide plus water. So you're going to end up getting two carbon dioxide and two water molecules in addition to those organic compounds. Another reaction that the alkene undergoes is the addition of carbenes. Carbenes are unstable intermediates, and the hybridization of the carbon of the carbene is an sp2 hybridization. So this is going to be planar. Now, carbenes has 6 electrons. So that is going to make the carbon of the carbene an electrophile. This carbon is electron deficient. So it is an electrophile. This is why it's very reactive whenever it's going to react with an alkene. There are multiple ways to make a carbene. The first way is by heating dinitrogen methane in presence of heat. Nitrogen will evaporate as a gas and you're going to end up getting your carbene. Now, once you get the carbene, then the carbene will be very reactive because the double bond is a nucleophilic. So the double bond is going to open up and it's going to attack the electrophilic carbon. So we said that this carbon over here is an electrophile. So it's going to attack the electrophilic carbon, and the lone pairs are going to close to make a cyclic structure. It's exactly the same concept as the bromination in this case. And your product is going to be a cyclopropane. So with carbenes, we're always going to make a cyclopropane. This is an example over here. And the addition, of course, of the cycle is going to be from the same side. Either you're going to form a cyclopropane up or you're going to form the cyclopropane down. And the double bond always opens up. It attacks the electrophile and the lone pairs on the electrophile, they go ahead and close. This is one way of making a carbene, like chlorocarbene. So another way of making a carbene is by using a chloroform or a bromoform. This is an HCCl3 or HCBr3 in presence of a base. The reaction is a simple acid-base reaction. So the base is going to come and take the acidic hydrogen here. This is acidic because it is very close to the electronegative element, so it is a partial positive hydrogen. So the base is going to take any of those hydrogens in there, create a lone pair on the carbon, and then one of the halogens is going to get kicked out, and you're going to end up getting your carbene. The difference between this carbene and the regular carbene, this is a very simple carbene which has hydrogens on it. So this is the simplest form of carbene. This is a dichlorocarbene. So instead of the hydrogens here, I am using a chlorine. And this is going to be the reaction. So you're going to start with your alkene and you're going to react this with a chloroform in presence of a base. So these two, when they react with each other, they're going to make the dichlorocarbene. And then the dichlorocarbene is going to come and attack. And as we said, that the first step, the double bond is going to open up and pick up the carbon, and then the lone pairs on the carbon, they're going to close in this case, and you're going to form a cyclopropane. But now in this case, the cyclopropane will have two chlorines on its carbons. Pay attention for the stereochemistry of the alkene in these reactions, because this is similar to the epoxide. When you close the cycle, you have to maintain the stereochemistry of the groups around the alkene. So if they are cis, then your product is going to be cis. If they are trans, then your product is going to be trans. Another type of alkene that you can form is by reacting the CH2I2 in presence of zinc, copper, and ether. All of those, they're going to form carbene. You're not responsible for the mechanism of this reaction. Just know that all of those are going to make carbenes, and the carbene are going to add to form a cyclopropane structure. The last reaction in this chapter is the hydrogenation. Hydrogenation is whenever you add hydrogen to the alkene in presence of a catalyst. So you break the double bond and you add hydrogen to each of the carbons of the alkene, and the addition is going to be a cis addition. So you're adding hydrogens on the same side. If you're creating a chiral center, just pay attention that you have to consider hydrogens both attacking from the back and hydrogens both attacking from the top in there. So over here, you highlight your alkene and you are adding two hydrogens on the alkene. So you are breaking your double bond and you are adding two sigma bonds in there. Because you are now going to create a chiral center in here, do not show the stereochemistry of the addition. But if you are creating a chiral center or if your double bond is locked in a cycle, then you have to show that the addition is going to be a cis addition. The catalysts that you are using in this reaction, they are either nickel, lead, which is adsorbed on a charcoal surface. This is why you have a C in there. So PDC means that it's lead adsorbed on a charcoal surface, or we can use platinum. So any metal can do the job. Without a catalyst, the reaction does not proceed. It's going to take a long time to proceed, so it will be a no reaction.